So we've seen that the first derivative tells us if a function is increasing or decreasing and finds these critical points, and which can become extremas, meaning minimums or maximums. Well, what does the second derivative tell us about a function and its graph? Let's investigate. Well, every function can be increasing and decreasing, and it also has what we call concavity. So if something is scooping up like this, like a cup, like if it rained, it would catch water, then we call that concave up. If something is bending down like this, like a frown, we call that concave down, all right? It's not, if it rains, it's not going to catch any water on that, okay? So a function can be concave up or concave down on an interval. Now, what's happening to the derivative at that point? Well, think about this graph here. Remember, the derivative is the slope of the tangent line or the slope of the function at a point. So if I have a tangent line right here that has a negative slope, right? It's kind of big, maybe, I don't know, negative 6, 7, 8 or something like that. And then I have another, pick another point down here. There's another tangent line. There's another tangent line there. What's happening to the slope of these tangent lines as we move to the right? Well, they're still negative, but they're getting less negative, right? This might have a slope of like negative 1/10, and this might have a slope of negative 10, all right? So they're getting negative, but they're getting less negative, so they're actually increasing. Can you see that? And eventually it'll be 0 at the minimum, and then that slope starts to get steeper and steeper and steeper, okay? So concave up means that the slope is increasing. So as that slope increases, we get a function, or we get a curve that is concave up. Now, if we look at the tangent line here, it's positive. Here it's still positive. Here it's still positive, but a little less positive. And eventually it's going to go to 0, right? And now the derivative is dropping, getting more and more negative. So the derivative, which is the slope of those lines, started out positive, then it went to 0, and now the derivative, the slope is negative. So the derivative is getting smaller. It is decreasing. So concavity is a measurement of the change of the slope. So it's concave upward if f prime is increasing. We are concave downward, the function is concave downward if f prime is decreasing. Okay, so increasing gives us concave upward, increasing first derivative, and decreasing first derivative gives us the concave down. Now, the rate of change in the derivative is the derivative of the derivative. Okay, so finding this change is finding the derivative of the derivative. We call that the second derivative. So we need to find the derivative of the derivative. Okay, so if a function is concave up, the second derivative will be positive. If it's concave down, the second derivative will be negative. Okay, and if it's linear, meaning there's no concavity, the second derivative will be 0. Okay? So the key here is this. If you want to find concavity, we need to use the second derivative, which will probably mean another number line. So when we're looking at a function and we're watching as a function changes, it can change in 4 different ways. And the graph can, that is. So it can increase and be concave down, all right? And if that's the case, then increasing means the first derivative is greater than 0, and concave down means that the second derivative is less than 0. Or we can be decreasing. That means that the first derivative is less than 0, and concave down, like this curve here. So that is going to be negative for the second derivative, less than 0. Okay. We could also be decreasing and concave up. So if something's decreasing, that means the first derivative is less than 0. If it's concave up, the second derivative is greater than 0. If we are increasing concave up, well, increasing means the first derivative is greater than 0. Concave up means the second derivative is greater than 0. So we have these 4 different combinations of increasing, decreasing, and concave up or concave down. All right, let's apply this to a function and see if we can find some critical points and some concavity. So here we have our function f of x equals 1/3 x cubed minus x squared minus 3x. Let's find the first derivative here. And so we're going to drop the 3 down. 3 times 1/3 is 1. And subtract 1 from the exponent. We get 2. And we get 2x minus 3. And we're going to factor that, which will be useful. This is x minus 3 times x plus 1. Okay. And we want to set that equal to 0 to find our critical point. So let's go ahead and do that. X minus 3, x plus 1 equals 0. And that happens at 3 and negative 1. Okay. And let's go ahead and make a number line here while we're at it, because we're going to need that. This is f prime. And negative 1 and 3. Let's plug in some numbers. Plug in a number to the left of negative 1. And let's plug it in to f prime of x. Probably plug it into the factored version, that's easiest. So maybe negative 2 here. So if we plug in negative 2, we're going to get a negative number times a negative number. And so negative times a negative is a positive. Now let's plug in something between negative 1 and 3. How about 0? Plug in 0. 0 minus 3 is negative. 0 plus 1 is positive. Multiply those, we get a negative. Pick a number bigger than 3. How about 4? So if we plug in 4, we get a positive number. Plug in 4, you get a positive number. Positive times a positive is a positive. So that tells us that we are increasing, decreasing, and increasing there, which means that negative 1 is a max and 3 is a minimum. Well, on to the second derivative. Now that's kind of review so far there. So now the second derivative is the derivative of the derivative. So let's find the derivative of this. You could do the factored version, but it's a whole lot easier if we go with this here. Okay, the simplified version. So we have 2x minus 2. And we're going to set that equal to 0. So we want 2x minus 2 equals 0. And that's going to be 1. Add 2 to both sides. Divide by 2. X equals 1. So now we need another number line for the second derivative. And it changes at 1. So what happens when we plug in something less than 1, like 0? Plug in 0 here. 2 times 0 minus 2. That is a negative number. Plug in something bigger than 1. That's 2. 2 times 2 is 4. 4 minus 2 is 2, which is positive. Okay, so the concavity changed here. So this means we have concave down. And this means, let's write down here, concave down, concave up. Well now, last thing we want to do here is we want to sketch a rough graph of this. Okay, so we just want an approximate here. So these things here tell us some stuff that's going on with the graph, right? So we've got x, we've got y. And it's nice if we have one anchor point. So let's pick an easy point like 0. Plug in 0. 0 to the third power, 0 to the second power, 0. It's all 0. So when you plug in 0, you get 0. That means this goes through the point 0, 0. Now, okay, we know that at negative 1, we have a maximum. We know that at 3, we have a minimum somewhere down here. And we know that at 1, the concavity changes. So that means that it's going to be concave up here, and it's going to change to concave down there. All right? Now, we didn't find these points exactly, so this is just gives an idea of what the curve would look like. Okay, now we're going to have a max here, a min there. If we wanted to, we could plug in 1, plug in -3, and find the actual heights, but we'll leave it at that for now. So we have a new type of point. We have minimums, we have maximums, and we have a point here that is the point where the concavity changes. We call that a point of inflection, or an inflection point. So an inflection point is this one where it changes from concave down to concave up. So here's a little definition. Inflection points are found if f is continuous on an open interval and includes c. So c is on the graph there, all right? Then the point c, f of c, is an inflection point if the concavity changes, okay, from upward to downward or downward to upward. So to find this, we can find a possible inflection value. So we're going to call this a possible inflection value. And that occurs when the second derivative is 0 or when the second derivative is undefined. Okay? These don't guarantee an inflection point, but they tell us where we should check. All right? So basically, these are the critical values of the second derivative. Okay? So it's important to note here, okay, if we have a change in concavity, but it happens at a discontinuity, then this is not an inflection point. So, all right, so what that means is this. If we have a graph and it's concave down here, and then at 0 it changes to concave up, but it is undefined at 0, then this is not, there is no inflection point at 0 because it's not defined at 0. So you can't have an inflection point if it's not defined. Make sense? So our test for concavity, this is called the second derivative test. Okay, so if we want to test, we want to first find any discontinuities, then we want to find the possible inflection values. That happens when the second derivative is 0 or the second derivative doesn't exist. Okay. And then we're going to put these on a number line and find out where the second derivative is greater than 0 or less than 0. Basically finding the critical values of f double prime. So that's how we use the second derivative to find concave up and concave down. All right, in the next video we'll do some examples here so you can see more detail how to work it out.